So since now we have seen how to calculate force in between charged particles, and if there is a multiple charge system, then how to calculate it, how the Coulomb's law is derived, and how it is useful to calculating the forces between different charges. So now in this sequence, let's move forward, and now we'll see that what is the concept of electric field and how we can utilize it and the role, its role in physics understanding and development. So electric field concept was given by Faraday, and now it has become the core concept of physics. So now let's see what it is and how to calculate different forces and the related physical quantities based on introducing this concept of electrical fields. So from our previous lecture discussion, if you remember, we have seen that if there is a charge q and let's say another charge q0, and they are separated by a distance r, okay, the force on q0 due to charge q can be calculated by let's say, let me represent it as r here, because that's representing the distance, the vector r for this. So the force r can be given as how 1 upon 4 pi epsilon 0 into q0 upon r square and r cap, right, where r cap is what? R cap is your vector r divided by the magnitude. Okay, so this is the unit vector. So this is what we have seen from our previous lecture discussion, that how to calculate force. Now just imagine that if this charge was not there, right, then why there some influence of this charge was there around, means what was there if this is not? It is like if there is some charge coming in the a particular distance from a given charge, then only these forces are acting, or there are something which is around, which is just causing the instantaneous force on it, right? So there comes the concept of electric fields. For example, let's say this is your point P, and the vector is let's say r. Then we introduce that, okay, we just give a concept of a distributed quantity, and that we call it field, right? Field. So it's a distributed quantity, and we can just assume that there is even if there is no charge here, there is something distributed quantity which can be vector or scalar or exist, and that let's say we call it field. And since this is due to charge, we can say that the quantity is electric field. Okay, so based on that, we can now see if this charge, and we just want to make this independent with respect to q charge. So we just, if you move out, then we can divide the whole equation like this, right? So let's say it can be 1 upon 4 pi epsilon 0 q upon r square and r cap, right? And then this can be the quantity from this force that can represent that, and then we multiply by q0, then we get the force, right? So we can write the force equation like this is equal to let's say some field, represent it as E at position R, and then multiplied by q0, right? So this way, this quantity we have just given approach of a physical quantity which is just exists there, even if this charge q0 is not there. If any charge is coming, so this field is working on it. So this is just a conceptual putting of it. We'll see that what is the physical significance and why we are trying to have a field definition, though we can just calculate directly forces from the Coulomb law. Right. So this separating out this equation, now we can have a force equation something like this, and this is the direction of the force would be radial. Okay. Now if you see that if it is the positive charge, then we will have r cap positive. If it is the negative charge, then we will have minus r cap, right? So it represents that if there is a charge and positive charge, then the field direction will be radially outward, right? And if this is a negative charge, then the field will be radially inward towards the charge. So this is another concept. You can just see that just we are giving to the field direction based on this the equation now we got, right? And there is a charge q0 which we can always multiply. So you just see that how the force concept have been just broken down into that some physical quantity representing field, and then here due to charge, so we call it electric field, and then multiplied by charge, which can give the force. So that way we can define if this charge, this Q0 you have in unity, let's say 1 coulomb, then we can say that electric field is that something, when if there is any point charge, the unit charge brought to a given point in the electric field due to charge Q, then it experiences the amount of force which it experiences, and that force is equivalent to that electric field, right? So that way you can define your electric field definition, and then SI unit of electric field can be given as Newton per Coulomb. Okay, so this is just see that we have just broken down that field equation into two parts, where we have just put the concept of electric field, which is some distributed quantity which is dependent upon, let's say, for a given charge the distance, right? So if you have a if you change the from a given charge, if you are bringing another other charge, and depending upon the distance from this charge, that field can vary. So that quantity, the vector quantity, the electric field would be a vector quantity, and that would be dependent on the position. So with the position, this field will vary, and that's the whole conceptual backing we have given it. Right. So now if you want to see, as we just saw here, that if you want to put a force equation, then now we can write that the force at point R can be given as let's say any charge, the Q, and then the electric field due to that given charge at point with which you are bringing. So for example, let's say this is your charge Q, and then this is the field because of this charge, and this field can vary with the distance, and depending upon R, if you have bringing one your charge, then that field will just experience a force, and you can have a Q0E, the vector R. Okay. So now this is the field of equation. So you just write in other way, you can write the force and the test charge which you are bringing. Now one important point here, when we are saying that field, then it is just the depending upon the position of that, at what position you are talking about the force you are going to calculate, right? So it means then the position of this charge due to which you are just estimating this field and trying to calculate the force for a given test charge, that should not change, right? So but from Coulomb's law, that if you bring any charge in the field, so the amount of force it is experiencing from charge Q to Q0, the similar and equal and opposite force will be experienced by Q due to Q0, right? So if it experiences 4, then the position of Q may not be be fixed. It may vary, because then if it is experiencing a 4. So to take care of it, we have to just consider that that test charge is very significantly small, and then you have some finite quantity given for electric field. So it means then you should have a limiting approach to it. So where you can say that electric field would be limit when the charge Q tending to 0, and the force will have some finite value, okay, Q0, right? So here just to remember that the field due to which we are talking about, that is producing the field around it, the charge which is called the source charge, and the field which is we are bringing to a given point in this field, the Q0, we call it test charge. So that we will keep using that test charge and source charge. So now you know that whenever we say source charge, I mean that is the charge which is generating the field, and when we say test charge, this is the charge which is experiencing the force for in a given field, right? So now you can see that the electric field is just dependent on the position. So in a different distances, the electric field value may change, and accordingly you will have, and that would be independent of that whatever charge you are bringing. Okay, so this is all going to be the complete property of the charge, the source charge which is generating the field, and the distance at which you are just trying to estimate the force on a given charge at a given point. So now let's see, as we have seen that if there is a system of charges, for example, let's say there is a point P and there are many charge lights, let's say Q1 here, Q2, Q3, Q4. Okay, so there are so many charges and we just want to estimate what would be the field due to these charges at a given point here. So as we just saw from the definition that each charge would have its own field, and then we want to have a resultant field from these all individual charges, and then how to estimate it, right? So as we just saw previously, like we are just defining the electric field from the concept of force and then dividing by the test charge which is going to experience the field, right? So similarly we can just utilize that concept where we are already know from our previous discussion that this forces of different charges at a given point, let's say we are bringing any test charge Q here, then they will experience the force Q0, and that force will be that individual forces due to all these charges and the vector sum of it, right? So similarly you can just have a force let's say at point R, and you can have a force R at point P. So let's say force at point P, then you can just say that force at P due to charge 1 plus force at P due to charge 2, force at P due to charge 3, right? So this is all we have seen that the superposition principle of forces and how we estimated force due to n charges similarly, right? So now just as we defined in our previous this discussion that we just divide the test charge and then it makes it independent of that and we just get our electric field. So similarly we can say that the electric field at point this R, and we just divide by the test charge, right? So we can have a P1 divided by Q0, Fp2 divided by Q0, similarly Pn divided by Q0, right? So that way you can just have your electric field due to different charges at the given point P here. So you can just write EP2, right? So see how you can utilize that same superposition principle and the force from where it have been derived, and you can have your own that electric field that would be a vector sum of it, right? So if I just want to give the equation, then it will be in a similar analogy. You can write 1/4 pi epsilon 0, and this is the charge due to different charges. Okay, so you can write the summation, let's say not summation for the example, let's say, so it is just because of Q1, so Q1 upon R1 square, let's say this is your RP1 square into RP1 cap. Okay, then you can have U2 RP2 square into RP2 cap. Similarly you can extend it to Qn divided by Rpn square into Rpn cap. Okay, this is how you can have a n charge system now, and then you can just find out with this summation you can have, and a summation of starting from let's say you can write from we are just counting from 1, so let's say it is from I equal to 1 to n, and then you can just write Qi upon Rp from charge I square into Rpi cap. Okay, so this is you just given a vector charge for n charges in the system, and you can estimate what would be the field similar in the analogy as we had calculated force, right? So this will have it will be as we discussed that direction with the field will be along the forces. So you can have EP1 here, we'll have here line joining this, so you can have EP4, this can be your EP2, and this can be your EP3, right? So that way, and you can calculate the forces, the electric field for due to different charges at a given point, and you can just take the vector sum, either you follow a component method or the parallelogram method as we do for forces. So that all going to be the similar format. So this is how you can calculate for system of multiple charges. Okay. Now the important point comes, that what is the physical significance. So now you may be wondering, we already have defined force, Coulomb force, and which is well enough to calculate the forces, and then why we need electric field, the concept of electric field, because it is even derived, this the concept of electric field is coming from that same equation force, right? So you may, in electrostatic you may not see that, okay, it is convenient to have it, but it is not necessary. But when we are moving beyond, when we are talking about electrodynamics, we will study the electrodynamics part, then we will understand more what we are trying to say and why we are interested in the concept of electric fields. But it becomes more relevant and more physically important in those cases when we are talking about moving charges, and then we are talking about electromagnetic waves moving, and with that some energy is getting transferred. So, and then instantaneous impact of forces due to these different charges in the system, and that cannot be explained if we cannot just give the concept of this that which Faraday given of the electric fields, and that becomes very, very important there. And even they are so their conceptual background in physics have become so important that they are just considered not just only the mathematical construct, as you saw that we just derived the electric field equation from the forces, which is actually the physical quantity, but even these electric forces, which are electric fields, have become the so conceptual important point in physics that they are now considered as a physical quantity, and they have their own independent dynamics, and they have their own laws, and they are governed, and even they are explained to explain to the concept of energy transfer due to the moving charges and all. So that terms becomes very important. Of course, not in electrostatic, if you may feel that why it is there, but when we are going towards the electrodynamics, they become much more relevant, and their physical significance is very, very important in those places. So that we would see when we are discussing about electromagnetic fields. So this is about physical significance. I think we have now the conceptual background of forces to electric field, and how to calculate if there is a system of charges, and what is the physical significance. So we'll see you again in the next lecture, where we'll discuss about electric field lines.